Hello. As part of the Micro and Smart Systems course, today we go to the one more topic related to the coupled modeling, and this has to do with electrothermal and elastic coupling. There are three different energy domains, and all these three are coupled to each other, and we will describe how one can model such systems. Earlier in the course, we had discussed the thermal loading or effects of temperature on structures. We will just recapitulate what we had done. We had actually discussed at length about bimorphs, that is, if you have two different materials that are attached to each other, because they both have different thermal expansion coefficients, the whole structure would deform. We had discussed that at length in detail. We are just going to describe what we had discussed very briefly before we go on to the topic of coupled electrothermal-elastic modeling. First, let us recall the definition of thermal expansion coefficient. It is the rate of change of strain with respect to temperature. One can define it as d epsilon by dt, where T is the temperature and epsilon is strain. So, alpha is a symbol we use to denote the temperature coefficient of expansion of materials. And because of thermal expansion, there will be a strain created in the materials, and that is given by the relation that we have shown over here. This is uniaxial thermal strain, meaning that in one dimension what will happen if I take a rod and heat it, it is going to deform by certain amount, and that amount leads to the mechanical strain, and that is given by alpha times temperature difference. If that happens in the material, let us say because of a substrate alpha S and alpha F, which is a film, that means that we take a substrate. All this what we had discussed earlier, we will just recapitulating it. If I have a substrate, over that I put a thin film of some other material, right. So, that is alpha F is the alpha of the thin film that we have put over that substrate, and the difference of those two will be the mismatch strain. Both of them actually expand by to different extents, and that is why there will be a mismatch strain, which we have denoted the difference of alphas between the two materials and the difference in temperature. And because of this, there will be a biaxial stress mismatch. So, epsilon mismatch is not multiplied just by E, but it should be multiplied by E by 1 minus nu for a situation such as this, which also we had discussed in one of the previous lectures. And if you think about what will happen to the strain in the thickness direction, if that is our thickness direction z direction, what will be the strain there? The strain there is given by alpha f times, of course, temperature difference, but also the Poisson effect coupled with this mismatch strain, and because of x and y there is a factor of 2, and nu is the Poisson's ratio, the same nu that occurs here and here. This will be the total strain for a beam that is sandwiched between a substrate, and there need not be another material over there, but if you were to restrict it, that is the strain it will have in the z direction. If it is free, then it will simply deform up or down depending on the difference, the temperature and the thermal expansion coefficients. But if you sandwich it, then this is the strain that is going to feel in the z direction, that is the thickness direction. Now, let us look at something very different from bimorph. So, if it is a single material, we have those relations that we just reviewed, but if you have two different materials that are attached to each other, and if I heat it, one of them wants to expand more than the other, it will bend. That is the bimorph effect or bimetallic effect, which we have discussed in detail. But now, let us consider a single material such as the one that is shown here. So, let us say that what we are looking at over here is a single structure, the top view. If I have the wafer, we are looking from the top. If it has certain geometry like this, if it is anchored over here and here, and let us say they are thermally also anchored in the sense that the temperature here and here is equal to the room temperature, and if you keep one of them at ground potential electrically and apply some potential difference between this point and this point, or that portion and this portion, then the current starts flowing through this structure. And since there are holes within the structure, the current has to go and then divide, probably little bit goes here and meets again, goes and splits, and then it comes back here and then it goes and drains out. Now, because of this non-uniform current, the ensuing ohmic heating or Joule heating will also be non-uniform, and because of that different portions of the structure will get heated up to different extents. If look at the color coding here, the red is very hot, this is the hottest, and blue of course the room temperature, that is relatively in this case is the coldest. In between there is a temperature gradient. But specifically if you look at what is going to happen to this structure because of this temperature non-uniformity, there will be a differential thermal expansion. We just learned that alpha is d epsilon by dt, but now T is varying quite a bit within the structure. So, accordingly epsilon will also vary and the structure would deform to achieve equilibrium, and in this particular case it will deform as it is shown over here. This is the deformed structure because under the thermal strain the structure tries to achieve static equilibrium and it is going to move like this. If you think of this as a gripper, here is where you can put something and it can grab it, or if you want to push on something, that is also possible with this. So, this we call embedded actuation, meaning that we do not have the actuator and the gripper like mechanism as two separate entities. The actuator is actually embedded within the gripping structure, a grasper or gripper structure. So, we can call it embedded actuation. It is not like an active material. This can be done with any electrically and thermally conducting material, and the key for this lies in the way the shape is obtained. Once you have the shape appropriately done, then it can create any behavior that you want, as opposed to piezoelectric, electrostrictive, magnetostrictive and other smart materials. Here the material is not smart, but the design is what is giving it the smartness that it is showing. We just apply electrical potential between 2 points and it just acts like a mechanical structure with the actuation given in it. How does it work? Let us take a very simple example where we are taking two beams that are connected serially. Okay, we call it a series connection. You will see the reason for that in a minute. We have this structure like this, and let us say this is mechanically anchored, this portion is mechanically anchored, and so is this. We have applied a potential difference between these 2 points. Let us say that this portion and this portion are at room temperature, so thermally grounded. What will happen when we apply potential difference between these two? One is that the current starts flowing like this, the beam is of uniform width everywhere, the current density is going to be the same and it is going to flow throughout, there will be ohmic heating, it is going to heat up, and that is not going to be uniform because these are room temperature, these are room temperature, whereas heat is generated everywhere. That heat has to go back to the substrate or through convection and radiation to the environment surrounding it, but nevertheless temperature profile is not going to be constant along this folded beam, but there will be something. What will happen to it? It will simply expand. It will simply expand. If I go back just a second, it will simply expand like this, because how much ever this beam deforms, this also will deform, simply expand. Now, if we introduce a little bit of asymmetry into this, as it is shown here, that is, we make this wider. We are making this portion wider than this portion. Now, if you look at the temperature distribution, it will be asymmetric. This part, this portion on this side will be hot, this will be cold. The reason is that the current that is going through this portion and this portion is the same, because whatever current goes here, the same thing has to go there. But the current density here is higher. So, this portion gets hotter than this portion to achieve equilibrium, because imagine that if I have if I were to have a bimorph, if I put those two layers together, if this is going to expand more than this one, it has to bend like this, because when it bends, this portion is going to have longer length compared to inner one, that is why it bend up like this. Here also it bends up, because this portion, because it is hotter than this, will try to expand more, this expands less, and it can give you this kind of motion. So, this is the principle. So, we have to use the differential expansion not achieved with different materials, but with the same material, but introduce an appropriate bias in the design by getting the geometry right. Then you can create this mismatched thermal expansion and make it move. It is in plane, it goes in the plane of the wafer. So, like electrostatic actuation, you can generate in plane forces very easily. If you want it out of plane, we can just use bimorph and make it go, or the same structure can be put in vertically and the structure can be made to move up. And now, if we compare the previous one, here we are applying potential difference between this point and this point, whereas let us say that we do differently. We will keep this at the same potential, that is this and this mechanically grounded, same electric potential, of course temperature is let us say room temperature, but this side is where we can electrically ground it. If we do that, then it actually moves this way. Previously slide you saw that it actually bends up like this, here it bends down. The reason for that is clear from the temperature distribution that we see here. This is the temperature distribution. You can see now this portion has become hot as compared to relatively colder or less hot, I should say, because it does increase in temperature, because you are passing current, it will be less hot compared to this side. And so, the hotter portion will expand more, so it has to bend down like this. Why does this portion get hot? Now, when you look at this and this as two separate resistors, more current will go through this, because the resistance of this portion will be less than this, because resistance is rho L by A. Here area of cross section is more than area of cross section here. So, the top portions resistance is going to be lower. So, that draws more current than this. So, the total current that comes here has to split from here to here, more current goes to this one rather than this, and that gets hotter than this other side, bends down. What it tells us is that we can take a structure, make holes wherever we want and try to get the type of motion that we want. Again, it is embedded actuation, and making this is rather easy in any microfabrication process that has a releasable structural layer, meaning that there should be one planar layer that is free to move in the plane. If you have it, and if you can have some electrode pads, we can apply potential differences and get the actuation that you want. Let us look at a movie that shows one of these actuators actually working. So, let us just end this and see that movie. Okay. Here is what you see, here is a little thin beam that is connected here and the wider beam that is connected here. You see this one is one of the probes, this other probe, faint trace of the other probe is here. Between these two we are applying the potential, and because of that there is a pad. So, separating it out, when you apply difference between these two, you can see this moving like this. This is serial connection, meaning current is going from here and going like this. Okay. You can actually see vaguely that it is getting hot, where it is the redness can be seen, and by applying a lot more voltage you can actually melt it. So, you can go to very high temperatures in these up to the point of melting. You can clearly see it moving this way and that way. The force in this will be quite large as compared with, let us say, electrostatic actuation. Okay. Now that we have seen a real device working, experimentally prototyped electrothermal actuator of this kind, let us look at some more issues related to it. Now, we saw that we can take this basic thermal actuator and introduce an asymmetry to take the linear expansion into the transverse domain. Instead of expanding just like this, it is going to expand like that. But this asymmetry need not be only in the geometry, but it can be, the structure can be symmetric, one portion is doped and other portion is not doped. Okay. So, this portion is doped and this one is not doped here. So, that way also you can change the electrical properties, because by doping, meaning that by introducing foreign species into a semiconductor material, we can change the electrical conductivity by orders of magnitude. If we do that here, again we are creating asymmetry, not in terms of geometry, but in terms of material properties, and we can make it deform as it is shown here. Okay. So, there are a lot of possibilities to design electrothermal actuators. We can take that basic thermal actuator that we saw in the movie also, which we observed just now, that it actually works. Now, if we take 4 of those, so if you look at this one, there are 4 building blocks within it, 4 building blocks, which is shown here. So, we have 1, 2, 3, 4, they are connected in a serial fashion. It comes from here, you apply, this is mechanically anchored. When you apply voltage between this and this, the current has to go, splits and then meets again, goes, splits, meets again, splits, goes there, meets and then splits again, meets and then goes. So, if you have something like that, the way you arrange them, you can actually get, you can make this move like this, 1, 2, 3, 4 are there. So, here is 1, 2, 3, 4, that makes it deform like this, you get lot more movement. In fact, what we could do is take a large block of this kind. Let us say that if we look at this large block over here, make these holes, very tiny holes. You see the holes, if I take this block over here, I just need to make these slits here. If I do that, several of them, it actually becomes like a linear actuator, because you can see how much this can move, how much it can move, that is from here it is moving till here, that is the actuation. Now, if you put several of them together, you get more force, and more important, you get more displacement out of this. You put them in parallel, you get more force, put them in series, you get a large stroke or displacement with this expansion block. One can also arrange them to contract, the same blocks that you have, you arrange them differently, there you can get contraction of this. Now, we show here those actuators 1, 2, 3, the stack of the electrothermal actuators connected with some flexures. These are what we call flexures, a central platform where we can apply different voltages V1, V2 and V3, one of them grounded, the other potentials above the ground. We can make this one move in the x direction and y direction, and also orient it in different directions. This again is a single layer. Any process that gives a single releasable structural layer is eligible for doing this, which pretty much any microfabrication process. So, once you have it, you can make these structures. It is a parallel manipulator, because you can position the thing anywhere in x and y within a workspace, and also can rotate, that is orientation can be changed. And it can be done with many processes, but one of the things that it's very easy to do is silicon and insulator layered process, where you take a SY wafer where silicon dioxide already is there, silicon substrate is there, the top silicon structural layer, device layer is there. You can dope it if you want and define different structures and get things like this. Here is a thermal actuator, here is a platform, here is an individual thermal actuator such as the one whose movie we just saw. And now, let us take a much more general scenario where we would like to consider a general object. Now, this is a general object, we do not specify a particular shape, it can be of any shape that people are interested in, it can be fixed, there can be 2 points or maybe different points where you apply voltage difference or potential difference, and you can have thermal loads, that is fluxes coming in, or there are sources at different points, you can have different types of boundary conditions thermally, and then you can have elastic problem where you can have mechanical forces of whatever kind, and also thermal kind of loads, if there are any, they can also be included. And with all those things, if you want to model such a structure, what do we do? In fact, we did not talk about the modeling of the simple heat actuator or the thermal actuator itself, but if you take a general situation, what do we do? So, for that, let us look at the governing equations, because as we noted earlier, modeling of microsystems is different because any microsystem device that you take is going to involve more than one energy domain. It is definitely 2 always, otherwise it is not going to be that interesting, and it will be more than that. This particular electrothermal actuation involves electrical, thermal and elastic, 3 different energy domains. So, we have actually 3 governing equations. This is the first one, electrical domain, and the second one thermal domain, and elastic domain, the third domain. So, first, second and third here. So, now if you look at what these governing equations, which at first sight may be intimidating, but they are all very straightforward. The first equation that we see is del dot, means divergence of K E times delta V. V is the voltage and this is the flux, electrical flux or current. K E is electrical conductivity or the reciprocal of the electrical resistivity, and this is usually 0 because there is no current source in the domain. So, essentially del dot K E del V equal to 0 is what we solve here, and then certain portions can have potential specified as it is shown, certain other portions may be electrical current may be specified also, and that is also indicated. Now, once you write this equation and solve for it, you will get the electrical current everywhere. Once you know that, we come back to thermal domain whose equation is similar, because just the way electrons flow, the phonon also flow, and both mechanisms are through diffusion. So, the equations look similar. If you look at this equation here and this equation, you can see the similarity. Wherever V is there, we have T, the temperature. So, it will be del dot K T del T, gradient T, and this K T here is thermal conductivity. K is electrical conductivity, K T is thermal conductivity, and then Q or Q dot one can say, because the units of that will be power, and that Q dot is K E times del V dot del V. This is the Joule heating, the electrical resistivity times del V dot del V, that we can put there, and then T equal to a temperature that is specified on part of the boundary, and other part you may have thermal flux that is shown here. Thermal flux can be convection or radiation, where heat goes out. If ambient is hotter, heat can come in also. So, here where is the coupling between this and this, because the voltage here appears over there, because that is the Joule heating or ohmic heating for this problem. You need to use that, do the thermal problem, and once you finish that, you have to go back to the elastic problem, because our interest is to look at actuation, how much does it move, and for that we have to go to elastic domain, where divergence of stress plus any body force that may be there, like gravity, centrifugal, equal to 0 is our equation, and the sigma is equal to stress times strain, and that strain, as we discussed at the beginning of the class, there will be alpha times T minus T naught, and where epsilon is the strain that we need to determine, and hence how it moves, that is given by this definition. Part of the thing we have specified, other part is because of this, if there were to be any mechanical traction load Fu on the boundary of the mechanical structure, that can also be taken into account. So, first we have to solve this problem and then solve that problem and then solve this problem. So, these two are coupled to each other. So, it is a sequential coupling, meaning first we do electrical analysis and then we do thermal analysis, and at the last we do the elastic analysis. And these two are sequential. So, the coupling is only one way, but it can be other way also, especially if you take the temperature dependent properties. For example, we have electrical resistivity can be dependent on temperature, and the QT is already depending on voltage, that coupling is already there between electrical and thermal domains, and then Young's modulus can depend on temperature and alpha can depend on temperature. We saw that temperatures can go very high in these things when we looked at the movie. And nonlinearity in this problem comes because of the properties depending on temperature. So, we have to redo this. If you did electrical and then thermal and elastic, after you get this and then if you find temperature is very high, then you have to go back and substitute there, evaluate these properties and come back again. For example, electrical resistivity dependent temperature, we do this and this simultaneously, or if Young's modulus depends on temperature, that also has to be taken into account. Now, we discussed what the equations are for solving. These equations have to be solved using numerical methods unless the structure we are considering is very simple. When you are doing numerical modeling, we also have to remember about this modes of heat transfer from the structure to the surroundings. One is of course is the conduction. It will go through the structure, go through the substrate and get the heat conducted away, but we also have convection, which is what is indicated here, and these convection heat transfer coefficients are highly temperature dependent, and in fact, they also depend on the size of the structure. What one can do here is, when you have a structure like a wide beam, if you want to know is convection through the top or bottom surface, we have to go to heat transfer handbooks and find what is called heat transfer coefficient, that is denoted with H, heat transfer coefficients. This can be for natural convection or forced convection, such as putting a fan and trying to cool something. Heat transfer coefficient. Taking this convection is very important, and this H itself might depend on temperature, and the size also may affect this H. If you go to a handbook and try to get a H from that for let us say a plate that is horizontal, heated from above, heated from below, whatever conditions, when you take that formula for use, we have to make sure that the assumptions made in deriving the formula do not have anything to do with size. If they have, then we need to pay careful attention to that point. And then the radiation. Radiation, there is this concept of view factors or shape factors depending on how the surface is oriented related to each other, and a heat, how it is going from one to the other or to the surroundings based on the radiation properties. And sometimes in a narrow structure such as the one that we saw over here, there will be small gaps. So, radiation can take place from one surface of this device to another surface. So, it is going to be quite complicated to account for the radiation. And the boundary conditions in this problem can be essential boundary conditions, meaning temperature is fixed. When we say essential or Dirichlet is where temperature is fixed. Okay. Natural boundary conditions are those where temperature is not fixed, but flux is 0. Then there will be different condition. Let us say that we have put an actuator, we put a thermal mass, big substrate, but in between we have put a very good thermal insulator. There is nothing like a perfect thermal insulator, unlike an electrical insulator, there are very good ones. Thermal, they are not that perfect, especially if the structures are very thin, interface layers are very thin, we cannot get a perfect thermal insulation. But if we do have that at one end, heat cannot be conducted away through that insulator to the substrate, then it gets hot within the structure, and one needs to worry about that as well. And sometimes in very narrow gaps, the air that is there, instead of convecting, it may start conducting. So, that also needs to be taken into account. There are a lot of other reasons why this convection is very important for this problem, and we will consider one example to show how dramatic the situation could be whether you model convection or do not model convection. The word here is model. Real structures, of course, there will be convection, it will do. Okay. So, if we take a structure that is I think it is easier to see the thing. So, again we have put a slit here, that is a narrow slit, and this is the place where between these two we are applying electrical potential, non-uniform heating, and according to this supposed to go up, the way this would bend that way, bend this way, it should go up, but actually it is coming down, as you can see when you model without convection. When we model with convection, it is actually going up as intended. So, we can see that whether you model convection or radiation effect will not be much until the temperature is very high, but this example shows that without convection, with convection you can get qualitatively different behavior, not just a slight error in the problem, but error in the solution, but the nature of the solution or nature of the deflection itself could be different. So, that is why it is very important to model convection properly and also the boundary conditions. So, here it is thermally grounded by putting a insulating layer, or not thermally grounded. So, you can have different boundary conditions and try to play with the geometry according to boundary conditions and the voltage level, potential difference level, we can make these structures work. And how do you analyze these things? One way is to use finite element model. Here you can see a 3D mesh, 3-dimensional mesh, all of these are brick elements that we can see, and it is fully coupled electrothermal analysis, and it is sequentially coupled to thermoelastic analysis, meaning that this is very time consuming for simulation, because the complexity of the structure, but it is sequentially coupled. First we have to say electrical problem, thermal problem, and then elastic problem. When you take temperature dependent material properties, it gets even more time consuming to simulate this kind of structures. A small case study can be done where we try out different boundary condition. EBC here stands for essential boundary conditions. Essential boundary conditions, and NBC here stands for natural boundary condition. Natural boundary condition. Essential means temperature is specified or fixed at the boundary. Here it means that flux at the boundary is 0. Okay. That is thermal flux. KT temperature thermal conductivity times gradient of the temperature, that is the thermal flux, that should be 0, then we call it NBC. If T is fixed to 0 or another value, it is essential boundary. If we try with various things and compare the maximum temperature, power input to the thing and applied voltage, if you take some parameters and fix them and compare, we will find that in each case temperature distribution is going to be very different, each of them behaves differently, and one can have a lot of design freedom in coming up with structures such as these. And one other thing we see here is that if you analyze, meso is 10 times larger than, meso is something in between, it is larger than micro. Here it is a scale drawing to show that at meso scale you get much more relative deflection than what happens at the micro scale. This is 10 times larger in size, also gives 10 times larger stroke or displacement for this case. And it can be done with other conducting materials also, but you have to make sure that the electrical conductivity and the thermal expansion coefficient are appropriate to make them heat up to reasonable temperatures and also hold up. The strength also comes in, so that it does not break because of this passing electrical current through this structure. And lot of data of one of the devices that was simulated and it is presented in a paper for different boundary conditions, different maximum temperature that will occur in the structure, and some more data where the tip deflection is being shown for an actuator of this kind, and there is some experimental data with large error in measurement, but nevertheless trend can be seen through the modeling. This was done with finite element modeling, where we first do electrical analysis, then thermal analysis, and then do the elastic analysis. Now, what happens if we have a more complicated geometry? All this that we showed, this complete data is for this single structure. So, this one structure is what was done. You can imagine that the number of elements that needs to have for very narrow structures and large structures, nothing can be ignored. This can take quite a bit of time. But now, what if we have this array kind of thing that we had earlier? So, there is 1, 2, 3, 4, 5, 6 building blocks that are arranged, where the current will go like this and then go like this, goes here, goes here, goes here, and then comes back. There are 6 building blocks arranged into this fashion, so that we can overall see some deflection like this. We already saw that this was used in a micro machined platform. One can do the analysis for this again using finite element analysis, but will take enormous amount of time. So, is there a way to do it in a simpler manner? So, let us look at a simple model, because we had done that for mechanical structures, we had done that for electrostatic structure. Mechanical structures, however complex it is, we can make it like a spring. However complex it is for electrostatics, we can make it like a capacitor. Similarly, for thermal problem, we can make it into a thermal resistor. Before that, first we need to think of them as electrical resistors. So, this particular thing, we have 4 parts. There is a segment 1 here, and segment 2, segment 3, and segment 4. So, we have 4 electrical resistors. R1 corresponds to resistance of this, R2 corresponds to resistance of this small element, then R3 is this wide beam segment, and R4 is for this flexure, which allows it to bend, and there is some electricity associated with that. Now, we apply voltage, we can find the current through it, and then compute electrical heating or Joule heating, and then do the thermal problem. Once we get the thermal problem, boundary condition can be put in, solve for temperature distribution, and then give to elastic problem. Again we take a beam, little beam here, another wide beam, and then the narrow beam. If we have that, we can use what is known as Michel's theorem. We have an expression for it in the subsequent discussion. This is like Castigliano's theorem. If your interest is only to find deflection at one point, you can just use this Michel's theorem to get that deflection, because our interest now is what is the deflection here. Once I do this kind of lumped modeling, I can do it for any complicated structure. Okay. Now, we are showing this here again, the narrow beam, connector beam, wide beam, and then the flexure, 4 parts, parameters in various ways. So, what we are basically saying this, let us take the size out. L is the size, so that you can analyze micro scale structure, a meso 10 times larger, or any other thing that we would like to have. So, now in this case what we are saying is this dimension is P 3 times L. So, we are keeping the P 3 as a proportion parameter, and likewise P 2 for this gap, and then this thickness also P 2, this length is P 1, and this in plane width is also P 2, and so forth. By introducing these proportion parameters, we can analyze this structure. The first thing is the electrical analysis. If I take the first one, the resistance, that is R 1, that will be rho L by rho L by A. So, here we have taken that, because there is P T P 2, meaning that there will be A will be the P 2 times L, that is in plane width, but also there is thickness which was P T times L. If you go back to thing, this is the P T times L is the out of plane thickness, because there will be L square and then top will be 1 here. If you look at this expression for R, it is inversely proportional to the size L, because phi E is simply the proportional part of it. This whole thing we are calling it phi E, that if you keep the proportion on, this is not going to change, and rho E is simply electrical resistivity, material property, and if you look at the resistance, that is inversely proportional to the size. The smaller the size, the higher the resistance. And the current here is potential difference, the V that we apply, that V over here divided by resistance, and we get this by substituting that into there, and then we can get the joule heating, the P E part of it, J square R, where J is the current density, which is voltage divided by resistance R. This is the current density, and times R will be the heating, or a Q dot term that we will have to put in the thermal problem. So, here we should notice that resistance inverse proportional to the size, whereas ohmic heating is directly proportional to the size. So, we have to remember the scaling effects, so that we develop some intuition for problems of this kind. And now, the Q dot, the J square R that we have is heat generated per unit volume. So, we are dividing by the volume also here, that goes as Q dot in the thermal problem. We have 4 segments. This is the heating source term in the first segment, second segment, third segment, and fourth segment. So, we have to put them now and derive a thermal lumped model, just as we lumped the first, second, and third and fourth beams. Of course, second one is very tiny little segment over there, but for all of those we did electrical resistor. Similarly, we can do thermal resistor. This is exactly the same, because the governing equation we saw earlier is based on diffusion process. So, electrons, the way they move, and phonons, the way they move, is both because of diffusion. So, we have the same governing equation and same lumped model also. Now, if you see, for each segment we can write a differential equation. We can ignore the second one, that is why we do not have 2 here, 2 is missing intentionally, it should be missing. It is not a typo, the 2 we do not consider for such a small one. Each of them will have a equation like this, which is a diffusion equation. Second derivative, d square T by dx square plus Q dot term, and the KT would multiply, because that is how the Fourier law of conduction would work. Now, if you do this, we will have integrating this equation twice for each segment, that is the first segment, third and fourth, we get an equation, there will be AI, BI 1, 3, 4, that is A1, A3, A4, B1, B3, B4, 6 constants. So, we need 6 boundary conditions and we have them. temperature rise at the left end is 0, give one boundary condition, and second one temperature rises at the interface of the first and third segments are equal, because whenever two things meet from this equation, this equation should have the same value, and thermal equilibrium of the second segment we need to have, because that what we ignored, that needs to be there is some heat generated within it, some enters, some goes, we need to account for it, and that is the third equation. And the fourth equation is temperature rises at the the third and fourth segments are equal, and then same thing at third and fourth segments flux continuity, heat flux continuity, and temperature rise at the end of the fourth segment is 0, that is another condition. So, we have 1, 2, 3 here, 1, 2, 3, and then 4, 5, 6 boundary conditions to solve for A1, A3, A4, and then B1, B3, B4 we can solve, and then if you look at the maximum temperature there in that will be proportional to this, and you can see that the size is missing here, it does not depend on L. If there were to be L, we will say it is proportional to the size, but here it does not depend, and the T max turns out to be this, depending on only the proportions of the thing and material properties and applied voltage. But remember that we have done this so far in a electrical and thermal coupled manner, but now we need to move on to the mechanical part of it. We would like to know what the deflection, it is going to bend up or down, how much is the deflection in this direction. Here we use what is called a Michel's theorem, which is the counterpart part of Castigliano's type of theorems that we have already discussed in our earlier lectures. Castigliano's theorem, it is a energy method based theorem, and that says that if you want a deflection there, you need to compute first the force here. If I have to apply unit force here, there will be internal force set up into the entire structure. That unit force causing internal thermal force in this, if you denote, this is the internal thermal force due to unit load, internal force, it is actually mechanical force due to unit load at the point of interest. When you multiply that with the mechanical strain alpha times delta T and integrate it for the entire beam from here till here, that is this whole thing, we get the deflection at that point. If this moves by delta, we get that. That is what the Michel's theorem gives, just like Castigliano's theorem and other energy methods work. Now, if you do that, delta relative deflection, if you take, it is going to be here. Again, it does not depend on the size, but in reality it does, because this is an approximation, that is what we have done. Reality is different. Here also, if we do not include convection, with include convection, relative deflection will change. Relative deflection here is only L0, it is size independent or scale independent, whereas if you take convection and look at the temperature, it is inversely proportional to the size, meaning the smaller the size, the larger the temperature. So, electrothermal actuation actually works more at small sizes, micro or 10 times larger, but not at macro scale. Although thermal loading is huge in terms of leading to cracks in buildings and making the bridges collapse, but when you actually want to make an actuator, its temperature difference is going to be inverse proportional to size. Accordingly, the deformation, everything will also be more at the micro scale, but again it depends on the properties, electrical resistivity, thermal expansion coefficient. If you have the appropriate properties for these two, a material can be used for thermal actuation. So, again we have the equations 1 to 4, and then we had neglected the segment 2 and took the heat balance anyway. Without convection, with convection we get a slightly different type of expression, and H here is the heat transfer coefficient. There is a lot to be modeled there to get the heat transfer coefficient properly, because as we said just a few minutes ago, that if you go to handbooks on heat transfer, they will give you the heat transfer coefficient for a vertical plate heated from this side or a horizontal plate heated from bottom or above, and all these different conditions, and are usually natural convection, mean that there is no fan to increase the convective heat transfer. So, once we get those coefficients properly, and there will be scaling effects also, we need to take that into account and then solve the problem. So, to summarize what we have discussed in the context of electrothermal actuators, one thing that we need to know is that electrothermal actuator gives us a way of embedding actuation into a mechanism. So, that if you have a gripper, there is no actuator pushing or pulling the gripper, rather the structure itself works both as an actuator as well as a mechanism, and can create reasonably large displacements and forces as compared with this only relatively, because we are not saying that we will get a large force like in our electromagnetic or IC engine, internal combustion engine type of actuation, but for micro scale reasonably large forces and large displacements, but it will be slow. What do I mean by that? If I want something to cycle, right. So, I apply potential electrical and then thermal coupling and then elastic, it will move. Now, I want to move back and I want to do this fast, and it cannot be done very fast, because it takes times to heat, cool, that normally at the micron dimensions it will take about a millisecond. So, we can go up to 1 kilohertz. That is one drawback of these systems. If you push it, you can go to 10 kilohertz, but not faster than that, because it does take time to heat and cool. And coupled modeling here is sequential usually, but when we include convection, because or when we take temperature dependent properties, things can become more complicated, meaning that we cannot do it sequentially, electrical first and then thermal and then mechanical. When you include convection, convection heat transfer coefficient also depends on temperature, and that also leads to nonlinearity, and the sequential coupling may be destroyed. And so, when you have large structures, we want to use reduced order modeling. There can be a large dimensional structure, but we will consider that as thin beams and make them as one dimensional electrical resistors, one dimensional thermal resistors, and then beams, and use energy theorems to quickly calculate the deflection. But this kind of reduced order modeling is not generally applicable, because if there is a slender structure, we can call it electrical resistor and then thermal resistor and then beam, but if it is a bulky structure and that is allowing for non-uniform electrical current distribution and hence thermal and then mechanical strain, it may not be amenable for reduced order modeling, where we have to definitely resort to finite element type of solutions and look at the entire behavior. This kind of coupled modeling is the characteristic of micro electromechanical systems or microsystems in general. So, in this course we only looked at electrostatic and mechanical coupling, and now we looked at electrical, thermal and elastic coupling, but there are a lot more things. If you look at the piezoelectric materials, which we discussed briefly in this course, there is material level coupling that needs to be taken into account, but in general any microsystems device that you take, there will always be coupling, and it will involve more than one energy domain, and at coupling what makes their modeling interesting. It also leads to a lot of advantages. From whenever something is difficult to model, we immediately see an opportunity for design, because it will lead to some interesting phenomena, and that we can take into account and take advantage of it to design interesting structures, such as the one that we saw in plane. If you want to move just with single materials, you can get differential expansion and get actuation. Okay. So, I will write my email address. If you have any questions, you can send an email. It is suresh at MECH ENG IISC airnet.in, and my name is GK Ananta Suresh. Thank you.